Alright, welcome to the new unit. It's Unit 3. Unit 3 is called Quantities in Chemical Reactions, and this is our first lesson of it, which will get you introduced to the unit, so an intro to the new unit. We'll talk about scientific notation, just as a little refresher. We'll talk about the conversion factor method from problem solving, some mathematical underpinnings to help you solve problems in this unit. We'll get into some actual chemistry, which is the mole concept and visualizing a mole of something. So we're just interested in getting a mathematical foundation today, and then talking about this new thing called a mole. And then we're going to continue on with that through the rest of the course, and indeed through the rest of chemistry. The mole is such an important concept for chemists that this unit is really, really foundational for what you guys are going to be doing. So let's jump into that intro to the new unit. So this is the new unit. It's called Quantities in Chemical Reactions. It's also sometimes called stoichiometry, so the study of quantities and masses in chemical reaction. Stoichiometry, you pronounce it stoichiometry. Stoichiometry comes from stoichion, which means element, so it's really just kind of measuring elements, stoichion. It's the basis for a field called analytical chemistry, and analytical chemistry is a very important field of work. It takes very, very precise measurements so that you can tell exactly how much of something you're going to need to get a reaction. Makes chemical processes more efficient. It identifies new chemicals and drugs. There's always a need for analytical chemists because they're checking in on a process, making sure that the right ratios are happening. If the wrong ratios are happening, they'll be able to maybe figure out what's going on and adjust the equipment and things like that. It's a field that's very useful. There's even a subtype of engineering called chemical engineering that combines this analytical chemistry with engineering, so that they're basically making their own apparatuses and things like that. So it's a really cool career path. So the math, in terms of math, we're really just kind of multiplying and dividing. The trick is knowing when to multiply and when to divide, and it's usually kind of common sense if you take the time to really familiarize yourself with these concepts, and that's what most of today's lesson is. If you notice, most of it is math, and only the last little bit is chemistry. So, please pay attention to these math skills that we're going to be working on and practicing, because getting that intuitive understanding of the math is going to really help you out for, hey, look, the rest of chemistry. So, the next 3 units and beyond. A quick refresher first, scientific notation. Scientific notation is a way of writing a very large or a very small number. Let's just as an example of why scientific notation is useful. We actually use this in everyday life. Right? If I wanted to write down how much money Jeff Bezos has, here's how much money Jeff Bezos has. It's like this much money. Right? It's 120. It's a lot of money. But we don't say 120000000000000. We say 120 billion. And we say this. Let me get my webcam. There we go. A webcam. So we say this. We say 120 billion. What we mean is, really, when we really break it down, it's 120 times a billion. Right? We have this thing called billion, and we know that billion is 10 to the 9. Right? 10 to the 9. It's that much. It's the 9 zeros there. 10 to the 9. So it's 120 times 10 to the 9. So it's a way to shorten this number, and that's what we see with scientific notation. In scientific notation, we wouldn't say 120 times 10 to the 9. We would say 1.2 times 10 to the 11, but those are the same number, right? It's just a way to shorten a very, very long number, a big number. It's going to get very important when we talk about the mole. And then there's a way to shorten very small numbers as well, which is using negative powers. So to review negative powers, right, when you have something to the power of something, 10 to the 3 is 1,000, right? 10 to the 4 is 100,000, right? 2 to the 3 is 2 times 2 times 2, and so on and so forth. When you have negative powers, 2 to the negative 3, it's 1 divided by 2 to the 3 kind of thing. And what happens here is if it's 10 to the negative 4, and 10 to the negative 3, it's 1 divided by, and 1 divided by 10,000, which 0.001 and 0.0001. And kind of a neat shortcut here that you can take is only when it's powers of 10 it's the number of zeros. So negative 4, 1, 2, 3, 4, right? Including that first zero, including that front zero. And then in 3 it's 0.001 because you can also do the hops, right? 1, 2, 3. The decimal point has to hop 3 times to get down to the last number. So that's what we get with decimals. And we've got 3 times 10 to the negative 3, you know that it's 0.003. If you wanted to do it kind of more naturally, you have 3, and the decimal point naturally sits here at the end of the 3. You can hop it 1, 2, 3 times. There's the new decimal point, 0.003. Another way to do it. So yeah, scientific notation does come up fairly often in chemistry because we're dealing with large numbers of elements, large numbers of atoms, and large numbers of molecules. So that's scientific notation, a quick refresher of it. Calculations with scientific notation. One of the reasons that scientific notation is really cool is because of powers of 10. You can use your power laws because it's powers of 10. If you're multiplying 2 powers of 10, I'll move this over to the other side. Multiplying 2 powers of 10, you can multiply the two numbers, and then you can also just add the exponents together, the 17 and the 14. Right, so 31, so you get 12.5 times 10 to the 31. It's nice because you can use your power rules. It's basically distributing the multiplication. And yeah, 12.5 times 10 to the 31 or 1.25 times 10 to the 32. It's kind of cool. Division works the same way. You can actually use powers of 10 for division. 2.5 times 10 to the 17 divided by 5 times 10 to the 14. You can just divide the 2.5 and the 5 and subtract the 17 and the 14. And you'll end up with 0.5 times 10 to the 3 or 5 times 10 to the 2. So that's kind of neat. Note that this is 5.0 times 10 to the 2. You might be wondering what's with the 0.0. We'll talk about that in a second. Okay, or you can just use your calculator. A lot of calculators have scientific notation built in. I'm going to try to zoom in on my calculator to show you an example of this. We're actually going to do, let's do this one, the 2.5 times 10 to the 17 times 5 times 10 to the 14. So I'm going to pause and get that set up. Okay, so I'll just show you how this works on my calculator. I've got one of these, TI-30. So here's our equation, 2.5 times 10 to the 17 times 5.0 times 10 to the 14. So I can actually put this in, 2.5. Okay, there's actually two ways to do this. Let's show the first way. You just use brackets. Brackets, 2.5 times 10 to the power of 17. Just make sure you've got it in brackets or else things are going to get weird. Times 5.0 times 10 to the 14. That's one way to do it, and you get the right answer, 1.25 times 10 to the 32. The other way, much faster, is I've got this button here. You can see it right there, EE. It's in blue. It's right above x to the negative 1. And when it's in blue, I have to hit this the second button to hit it. So 2.5 second function, that, there's my little e. Now that e takes the place of times 10 to the, and I get 17. That's 2.5 times 10 to the 17 times, and then 5 times 10 to the 14, 5, 10 to the 14, and I get the same number. So this makes this E button makes my calculator treat that whole thing as scientific notation. And many calculators have that button, so you just have to kind of search for it. Sometimes it's E, sometimes it's EXP, sometimes it even says times 10 to the, and it's kind of nice. Yeah, very, very useful, especially when you're doing divisions and things like that, so you don't really get lost in your scientific notation. So mine's there on this calculator. Have a look for it on your calculator. If you can't find it, or if you want to know how to find it, just send me a message, give me a picture of your calculator, I might be able to help you figure it out. Alright, moving back to this. Calculators, scientific notation. This is a different one, a Casio, and you can actually see the exponent button. That one's just a full-on button on this calculator. You don't even have to hit second function for it. Yeah. So how about extra zeros? Why is there zeros after? It helps us say how precise the measurement is. Basically, if I measure 5 centimeters, but my ruler was in millimeters, I can say I measured exactly 5 centimeters, but I want to tell people that it measured to the millimeter, so 5.0, right? Or if you have 200 millimeters, but it's to the millimeter, you can measure exactly 200 millimeters, and it would be 2.00 times 10 to the 2. These are called significant digits. We're not going to get too hung up on sig digs. That's, it's important, but I'm not going to worry too much about them in this course. Physics, really, really big deal in physics, and big deal later in chemistry as well. Just be aware that they're there. For me, just round it to the 0.01 or to the percent, to the single digit percent. That's fine. Okay, next up is conversion factors. So this I'm going to pause and actually set this up. Okay, next we're talking about conversion factors, and this is my recommended method for doing calculations in this unit because it's fast, it's snappy, and it really gives you an intuitive feel for what you're actually doing. And to promote that, if you look up here and keep in mind, I'm not giving you guys any formulas in this unit. No formulas. I will give you hints as to how to convert things, but no easy peasy algorithms. I want you guys to get a feel for this math. I want you guys to get a feel for the process that we're going to go through. So yeah, no easy formulas, no magic triangles with me. This is conversion factors. Sometimes it's called the unit factor method, factor label, dimensional analysis, whatever. It's wonderful as long as you have conversion rates, and we are going to learn about various conversion rates today. So let's talk about what a rate is. A rate is something over something, usually written with a slash, and you've seen these in your everyday life. Kilometers per hour, it's a speed. Kilometers per hour. Percentage per assignment, right? It doesn't have to be a round number either. 2.54 centimeters per inch. 3 feet to a yard. All kinds of conversion factors. So that's a rate. A conversion factor depends on a rate. Conversion factor depends on having a rate. And rates are reversible. So 80 kilometers in an hour, 80 kilometers per hour, the speed means that in 1 hour, you're going to drive 80 kilometers, right? You can just reverse the rate. When you reverse the rate, you can just flip the fraction, right? Just flip the fraction. So here's how you solve one. You can write initial quantity, you can think about what the final unit should be, and then you set your rates. You multiply it. So to give you an example, here's an example. Car has a fuel efficiency of 5.8 liters per 100 kilometers. That is a rate, 5.8 liters per 100 kilometers. That rate tells us every 100 kilometers, we're going to use 5.8 liters of gas. Right? That's our rate. Or if you reverse it, if we drive 100 kilometers, we're going to use 5.8 liters of gas. Right? Or if we use 5.8 liters, we've driven 100 kilometers. It's reversible. It's a rate. It's a fraction that can be flipped. What distance would the car drive with 25 liters of gas in the tank? So we're going to go over to our this guy, and we're going to solve that. So here's the basics of a conversion factor problem. We have our rate, 5.8 liters per 100 kilometers, and we have 25 liters of gas. We want to, convert, right? We want to convert liters into kilometers because we have our rate. We have this thing that lets us convert it. It's important to note that this thing is reversible. This is 5.8 liters per 100 kilometers, or 100 kilometers per 5.8 liters. You know, fractions work like that. We can flip our fractions, and they maintain the same ratio. I want to convert 25 liters of gas to some amount of kilometers. Two ways to do this. There's two ways to do this. We're going to go through both. This is the way that I prefer. You start with your 25 liters, and we're going to be multiplying, and we're going to come out with an answer in kilometers. Some amount of kilometers. We know we want some amount of kilometers. That helps us decide which one of these two rates we're going to use. Right? How do we get, when we multiply fractions, right, we can start canceling things out. And what we're going to cancel out is the units. We have to look at our units here, liters. Right? Liters. To cancel out liters, we want the other liters to be on the bottom because we can cancel top and bottom. So we can put 5.8 liters underneath, which means our liters is going to cancel. It's going to leave us with kilometers, 100 kilometers per 5.8 liters. And we just throw that through our calculator. We can actually put that in the calculator directly. All right, on 25 times 100 divided by 5.8. I get 431 kilometers. 431 kilometers. So once again, the flow here is that I look at my unit, 25 liters, and I choose which of my rate fractions, which one of these will help me cancel out my initial unit, liters to liters. It helps me figure out whether I'm multiplying or dividing, right? So which one of these fractions to use? I chose this one. If I was going the other way, if I had a certain number of kilometers to travel and wanted to figure out how many liters, I would flip this. I'd go the other way. So that's the first method, and it's my favorite method because it never steers you wrong. The other method is to do the cross multiplication. And in that case, it's easier. Let's put x. We've got x kilometers. X kilometers for 25 liters. It's easier to have your unknown at the top because that way you don't have to divide by anything when you're solving it, right? You're just going to bring one thing over, equals. And then we have to choose which of these is going to match this fraction. And hey, look, it's the same one we chose earlier. 100 kilometers per 5.8 liters. And then to solve this problem, all we need to do, because it's x is over here and we're dividing by 25, we multiply by 25 on both sides. 25 liters times that, and that times 25 liters. And we'll get x kilometers is equal to 100 kilometers times 25 liters divided by 5.8 liters. Hey, look, liters cancels again, and it's actually mathematically identical. X is equal to 431 kilometers. Mathematically identical as the one that we did before, right? If I wanted to put it in 100 times 25 divided by 5.8. 5.8. Yeah, so that's a conversion factor. And you can actually chain these. You can chain conversion factors, which is really, really nice. So we'll be doing that in chemistry. But yeah, please learn this math. Please do lots of practice and learn that, because I'm not going to give you any formulas. You have to intuitively understand this on your own. We will do lots of practice problems, so you'll get lots of practice with that. Yeah. Here's another example of this this type of thinking. How many seconds are there in a year? Right? How many seconds are there in a year? Let's look at our setup. We have 1 year. We have 1 year, and we want to know how many seconds, right? How many seconds? And I can do conversion factors to do this. I don't know how many seconds are in a year, but I do know how many days are in a year. And my year is going to be on the bottom. That way, year is going to cancel. Year is going to cancel. 365 days per year. There's 5 days per year. Now, I don't know how many seconds are in a day, but I do know how many hours are in a day. 24 So again, days on the bottom, 1 day, because my day is going to cancel. Hours per day, right? Same thing, I know how many, how many somethings per hour. Well, I know that there's 60 minutes. And I know per minute, because I want to cancel my minutes, that there are 60 seconds. And so you have this kind of train of canceling. Year cancels year, day cancels day, hour cancels hour, minute cancels minute. We convert years to seconds. We have to multiply by 365 times 24 times 60 times 60. And there's the thing. It's about 31 million seconds. 31 million seconds. 31.5 million seconds. Let's work backwards. How long is a billion seconds? Well, here's where the unit factor method shines. How long is a billion seconds? We start with 1 billion seconds. We're going to just go 10 to the 9 for a billion. 10 to the 9 seconds. 10 to the 9. And I want to multiply it by a bunch of things, and I'll end up with how many years? Right? How many years? Well, 10.9 seconds. I can go through the whole process again. I want seconds on the bottom. And now I'm going up. I'm going up in times. So I know that, if I want to go to day, well, maybe not day. Let's go to minute. Right? How many minutes in seconds, right? What's my ratio? Well, 1 minute is 60 seconds. So 1 minute is 60 seconds. So now instead of multiplying, I'm dividing. But note that it came out of the math. It wasn't something I remembered. I have to divide because that's the thing that puts seconds on the bottom. 1 minute per 6 seconds. Now next, I want minutes and maybe hours. Right, that's 60 minutes, 1 hour. Next up, from hours, 24 hours in 1 day, and 365 days, 1 year, equals some amount of years. And we could do that process. We could divide by all of them, or you can divide by all of these multiplied together. That works too. But that's the general method. Or we just worked out that 1 year is 31.5 million seconds. Right? 1 year is 31.5 million seconds. That's a rate. Right? We get to keep that rate. We can use it. It's a rate. It's always going to be the same. So we can just use that. 10 to the 9 seconds times, now my seconds is going to be on the bottom, 31.5 million seconds. Million seconds on the top is 1 year, and I can get an answer in years. There are different ways to solve this problem, but they all involve rates, and they all involve having our top one match the bottom one. Our top unit matches the bottom unit, so that we can cancel the units along the way and end up in whatever unit we're finishing with. That's conversion factors. That is conversion rates. I'm going to be using that throughout to solve problems. Yeah. So that's conversion factors. Next up, the mole concept. Oh, by the way, the answer is 31.7 years. It's a billion seconds is 31.7 years. I'm going to be there pretty soon. This October, I'm going to be a billion seconds old. It's kind of weird to think about. So next up is the mole concept. Here's a question. I gave you the mass of an atomic mass unit, 1 AMU. Water molecule has a mass of 18.02 AMUs. And a glass of water has 250 grams of water in it. So the question is, how many water molecules are in the glass? Notice that this is a very small number. 10 to the negative 24 is tiny. So I'm going to pause. I'm going to set it up over on the whiteboard, and we're going to get into it. Okay, so I've set it up. we start with 250 grams of water. We know that 1 AMU is 1.66 times 10 to the negative 24 grams, and 1 H2O is 18.02 AMU. These are rates. We can turn them into fractions. Right? We can turn this into 1 over 1.66 times 10 to the negative 24, 1 AMU per that grams, or the other way around, or 1 over 18.02, or 18.02 over 1. We can go either way. And we start with 250 grams of water, and we want to figure out how much H2O, right? How many molecules of H2O do we have? So we start with grams. And I've got grams here. To convert it, I want my grams on the bottom because I'm going to cancel it. I'm going to cancel it on my way over to how much H2O I have. So that puts my 1.66 times 10 negative 24 on the bottom. And it's going to cancel out to 1 AMU. Right? And then I'm still not in, that's going to give me to AMU because I'm going to cancel my grams. I'm going to cancel my grams. Now I'm in AMU. And then going over here, 1H2O 18.02 AMU, same concept. I want to cancel my AMU, so this has to be on the bottom, 18.02 AMU. And my 1H2O has to be on the top. And so my answer is going to be 250 divided by 1.66 times 10 to the negative 4, and then divide again by 18.02. So let's do that. Let's throw it through the calculator. And hey, look, we need to use our scientific notation skills. So I'm going to put in 250. I'm going to divide it by, now 1.66 times 10 to the negative 4, I put 1.66. Do my second function e thing, e. So you see that e there. Negative, it's the special negative, that negative 24. That. I'm going to divide it again, right? Divide again because the 18.02. There you go. 8.36 times 10 to the 24. 8.36 times 10 to 24 H2Os. That is a lot of molecules of water, right? 8.36 billion? Yeah, I think so. Yeah, that's a lot. So yeah, big amount of water. But you see here how the conversion factor method helps us figure out how to arrange our rates that we know into a problem that lets us solve for the for our answer. We're going to get a lot of practice with that in the class. Yeah, so that's our answer. And if we jump back here, if only there was a better way. Well, there is. This guy, Avogadro, Amedeo Avogadro, but here's his actual full name: Lorenzo Romano Amedeo Carlo Avogadro di Quarenza e di Cereto. He created this concept called the mole, right? He figured, hey, you know what? Why don't we have a number that represents a certain pack of molecules, right? Like billion or trillion, but for molecules. And that's the concept. It's a way of counting atoms or molecules. And in fact, the word mole comes from molecule. It's like 1,000 or million, describes how many of something we have. And it's actually, there's an international definition of mole is this many. That much is a mole of that thing. And it doesn't matter what it is, right? A mole of grains of sand, a mole of anything, a mole of atoms, a mole of molecules, whatever. It's like a pack of something. Or my favorite thing to compare it to, I bought some bagels, right? I buy bagels by the dozen. I go into the shop, I say, give me 3 dozen bagels, and they give me 36 bagels. I use this shortcut, dozen, because bagels come in packs of 12, or maybe 6. You can have half a dozen, you can have 0.5 dozen. But, it's understood, everybody understands what a dozen is, and so that's what the mole is to chemists. The mole is a number that we all understand, that we all share this number of 6.02 times 10 to the 23, this big number. And it helps us describe these big numbers, like this big number that we got here, 8.36 times 10 to the 24, is very, very, very large. But if we put it in terms of moles, it's like 14 moles or something like that. Much easier to talk about. Right? Just like saying, give me 3 dozen bagels, and then the person's like, okay, here you go. Instead of saying, give me 36 bagels, and the person has to like count through 36 bagels. It's a shortcut, and it's a great shortcut, and everybody uses it. So, yeah, that's the mole. And yeah, it's really just a way of talking about numbers of particles in a way that we could relate to them. They tried different things at the start because they were interested in gases. They used hydrogen. They used the amount of hydrogen that weighs 1 gram. But then that turned out to be really difficult to figure out, so they moved over to the number of carbon-12 atoms that weigh 12 grams. It was easier to get carbon-12, I guess. Anyway, that's 1 mole, and that ended up being this big long number here, ish. This is now internationally defined as exactly that number. That's called 1 mole. It's sometimes also called Avogadro's number, from this guy, Avogadro. Yeah, so that's a mole. A mole is a pack. It's like a dozen, except for instead of a dozen, it's that many. And you can have, because it's so big, you can have, 0.357 moles. You can have 2.3 moles. You can have 2.17 moles. And you can have, a bunch of different ones. And a mole is really tremendous. If we want to visualize it, visualize a mole. Imagine making the entire planet in Minecraft, right? This is, I think someone tried to make like Yosemite in Minecraft. Imagine making the entire freaking planet Earth in Minecraft, the whole planet. Even like the core and everything, like the ball, right? The whole ball of planet. That would take somewhere, because each Minecraft block is 1 cubic meter, would take somewhere on the order of 1 times 10 to the 21 blocks. So this is 1 times 10 to the 23, 6 times 10 to the 23. The whole world in Minecraft, 1 times 10 to the 21 blocks. That's 1 with 21 zeros after it. So make the whole world in Minecraft. That's how many blocks. And then do that 600 more times. And that's a mole. It's 602 planet Earths made out of Minecraft. That's the number of blocks in a mole. It's an insane, it's a tremendous amount of something. It's also about how many grains of sand there are on the entire planet. So imagine like taking an airplane flight over like the Sahara Desert and think about each individual grain of sand. You're getting pretty close to a mole. And it happens to be about the amount of atoms in a coin. A typical coin has about 1 mole of atoms in it. So just think about just how many little tiny atoms there are. Imagine taking all of the grains of sand in the world and turning it into a giant coin, and then flying over that in an airplane. Like, it's a tremendous number. Huge amount of atoms, huge amount of molecules. Right? So think about that, like the amount of grains of sand in the world. Massive number. And it turns out there's about 14 moles of water in a glass of water. So think about, all the grains of sand in the world times 14. That's how many water molecules, individual water molecules, are in a glass of water. And that's the tremendous size of the mole. But we can also see that this mole concept makes numbers easier to talk about. We have so many particles in that glass of water, but we can just say, oh, there's 14 moles. There's 14 packs of molecules in there. 14 Sahara deserts worth of particles. That's the power of the mole concept. And there's a conversion factor, obviously. You just take that Avogadro number, 6102 times 10 to the 23, per 1 mole of something, and you can flip it back and forth. You can decide, you do this kind of stuff with it. In fact, we could actually take this and prove that it's a mole, right? 8.36 times 10 to the 24 molecules of H2O, individual little H2Os, and then we know that on the bottom we want the molecules, 6.1 times 10 to the 23 of anything, and it's 1 mole. 1 mole is 6.02 times 10 to the 23 of anything, and so we can just divide, and that's about 14 moles. In fact, let's actually say exactly how many moles it is, because I don't want to be rude. 8.36 times 10 to the, that's my little e, 24, divide by 6.02 times 10 to the 23, 13.887. So it's not, I guess, about 14, but it's 13.887. Just like I can have, $2.75 million, I can have 13.887 moles, because that represents, 13 amounts, 13 packs, plus another 0.887 of that huge, gigantic number. Alright, so back to this. And some people celebrate Mole Day. Chemists will sometimes celebrate Mole Day. It's kind of like Pi Day, where Pi Day is 3.14, so March 14th. Mole Day is October 23rd, because of 10 to the 23. 10 to the 23. So another nerdy day that you can celebrate if you want. And 6.02, because it's 6.02 times 10 to the 23, Mole Day starts at 6:02 in the morning and it finishes at 6:02 at night. So it's only a 12-hour thing. So yeah, Mole Day is another nerdy little celebration. That's the end. Let's talk about what we talked about. We did the intro. We talked about scientific notation and how to put it into a calculator with your little E button. Talked about the conversion factor method, which is what we're going to be practicing in class, doing lots of conversion factors. Then we talked about the mole concept and visualizing just how big a mole of something is. And really keep in mind that it's like a pack of something. It's going to get so much easier if you get that intuitively into your head, that a mole is a pack of chemicals, that we internationally agree that that's what we're going to call one pack of chemicals. We just have this word called mole that describes it. Yeah, that's it for the start of the unit. Lots of math to come. And well, really more lots of arithmetic. We pretty much got through all the math today. Now it's just applying it to the various concepts in chemistry. All right, that's it for me. I'll see you guys in class, and yeah, bye.